Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. In this episode of our Deep Learning Indaba Series, we're joined by Herman Kamper, lecturer in the Electrical and Electronics Engineering Department at Stellenbosch University in South Africa and the co-organizer of the Indaba. Herman and I discuss his work on limited and zero-resource speech recognition, how those differ from regular speech recognition, and the tension between linguistic and statistical models in this space. We dive into the specifics of the methods being used and developed in Herman's lab as well, including how phoneme data is used for segmenting and processing speech. Before we jump in, I'd like to send a big shout out to our friends at Google AI, which recently opened up applications for its 2019 residency program. The Google AI Residency is a one-year machine learning research training program with the goal of helping individuals from all over the world and with a diverse set of educational and professional backgrounds become successful machine learning researchers. Find out more about the program at g.co/AI residency. And now, on to the show. All right, everyone, I am on the line with Herman Kamper. Herman is a lecturer in the Electrical and Electronics Engineering Department at Stellenbosch University in South Africa and one of the organizers for the recent Deep Learning Indaba event. Herman, welcome to This Week in Machine Learning and AI.
Oh, thanks a lot for having me.
I guess we should start with the Indaba. The event just finished. I saw an incredible flow of tweets from the event. It looked amazing. From your perspective as an organizer, how did it go?
I think it went pretty well. I think obviously as the organizers, we're a lot more aware of the things that might break behind the scenes. But overall, it was really successful. I enjoyed it a lot. And from everything I've heard from all the people that was here, I think that's where we got the biggest encouragement, just people telling us how much they enjoyed it and how much they got from the event. So I think it went well.
And the highlights from your perspective?
That's very difficult. I think maybe three things that really stood out for me. It was two talks. The one was by King Yong Cho. He led sessions on basically the fundamentals of building natural language processing systems. And that, to me, was just amazing, the amount of kind of dense content that he packed into a lecture, but then also giving kind of his high-level overview of kind of where the field is going. That was one big thing. The talk by Jeff Dean at the end, that was just amazing. And then the poster sessions, which was basically students from across Africa presenting their work. And I've been lucky to be at international conferences. And this poster session at this African event was just amazing to see the quality of the work and that the students here are doing.
That's fantastic. Before we dive into some of your research, why don't we have you introduce yourself to the audience? You are relatively new on the faculty at Stellenbosch. Tell us a little bit about your background.
Yeah, so I'm actually a Stellenbosch boy, kind of born and bred. I grew up here. I did my undergrad and a master's here. And then I also worked for a bit, and then I went to Edinburgh to do my PhD there in the School of Informatics. And that was really amazing in Scotland. Really struggled with the weather there, but other than that, it was an amazing experience. And then I did a postdoc in Chicago for a relatively short time, for about a year at Toyota Technological Institute. And I mean, I grew up here, so as soon as I left, I kind of was campaigning already to come back. I really saw my kind of long-term goals to come back. And while I was doing my postdoc, I was very happy to get the appointment here.
Actually, I have a question about TTI Chicago. Is that relatively new, or is it affiliated with another school? I lived in Chicago for many years and never heard of it.
Yeah, so it's fairly new. It's really like an institute. It's kind of a lab. It was funded by Toyota initially, but now it's kind of on its own. And it's a lab that's affiliated with the University of Chicago, and it's a kind of a research-only institution. So you can do a PhD at TTI Chicago, and they do a bit of postgraduate teaching as well. It's actually an amazing place for specifically machine learning. It's quite a small group, but it's very tight-knit. So you have great people in kind of theoretical machine learning, theoretical learning theory, and then also speech processing, natural language processing, and computer vision.
So Herman, your research is focused on speech processing. In particular, you're concerned with how to do speech processing when you don't have a lot of resources. Tell us a little bit more about what that means.
Yeah, so actually this already started while I was doing my master's. When you want to build speech processing systems, which I think can really improve people's lives, this works well for English and for German and for Spanish, because big companies are invested in these languages. And what they do is they collect a lot of annotated data. So they get people to say things, and then they transcribe it as well. They give labels to basically the input speech. But there's so many languages on Earth that it's basically impossible to do this for all the languages. So my research focus is really on very low resource languages for which you just don't have that much data, and annotated data, so data with labels, and actually languages for which where it might actually be impossible to get these type of annotated resources. So there's a large proportion of the languages spoken on the Earth that doesn't even have a written form, so you can't write them down. And if we want to build speech systems for these type of languages, or if you want to maybe kind of preserve or document these languages, a lot of these languages are dying out, and you want to build kind of speech processing systems that's able to look at these data sets, then you're in the setting where you basically don't have any labels at all. You just have a collection of speech audio, and what you're trying to do is kind of find the structure in the raw audio, and to do this without any form of supervision, any signal. So we call this unsupervised learning. I think a lot of the listeners might know this, and kind of try to find the raw structure in the audio without any guidance. And this really has application. It kind of has this double motivation. The one motivation is that if we can crack this problem, we can build speech systems in settings where it was just not possible before, for languages that we just can't build systems for at the moment. And then the second motivation is that a lot of the people that's interested in these kind of unsupervised model are also interested in how humans learn language, because human infants, in a sense, they never see any texts, labels. They don't get any hard supervision. They're kind of just bombarded with this stream of audio. And from that, it's kind of a miracle how they then start to learn language kind of automatically from just this raw sensory input. So people, they call it zero resource speech processing sometimes, and people that's interested in this area normally has this double motivation of either building speech systems, practical systems, or actually using these type of models to investigate language acquisition in humans.
When I think about the trajectory of speech recognition systems over the years, there was this transition from kind of strongly linguistic-based models to more statistical models. Does the fact that we don't have labeled data kind of push us back towards linguistic-based models, or are we still able to operate in the statistical domain?
That is an extremely interesting question. I think a very, very good question, because it's something that I think this unsupervised community, this unsupervised speech community is actually struggling with, is this question. And I think, so I can kind of say from a practical viewpoint, a lot of the systems are still very, of the, I'll call it zero resource speech processing systems, although I might not like the term, but a lot of these zero resource systems still operate in the statistical domain. So how you can think about that is, if I give you a ton of data or a collection of data and I ask you to describe it statistically, then that's basically what it boils down to. At the same time, I think people in this field are becoming more and more interested in kind of what is the structures or what is the small things that you need to build into these systems in order for it to actually learn something. So you might have a statistical system, but you can put in specific cues that it can pick up on. And I think the reason this question is so interesting is if we can figure out what type of cues, what type of extra structure, what type of biases we need to build into our unsupervised models for it to actually learn language, if we can answer those questions, what are kind of the minimal things that we need to put in, then that might tell us something about how the type of cues that human infants use to do this. And it's really interesting because it's also the converse. So people actually are people in this field keep a close eye on cognitive studies, cognitive psychologists who actually try to answer these questions on infants. So we try to read a lot of literature from that side, which tell us what type of cues do humans use. And in the cognitive literature, there's a lot of studies that look at what are the cues that infants use and how can we use some of those ideas and build those into our systems. I think really what this community is doing is actually seeking the answer to that question. What are the things that we need to explicitly build in, and what should we just let a model learn?
Right. I think it sounds like in this field, as in some other areas in machine learning, there's kind of a pendulum that's swinging that, we started with these very strongly, physics-based or model-based approaches, and then we kind of swung hard to statistical-based approaches. And now folks that are kind of on the frontier, or many folks, not all, are trying to figure out ways to incorporate the models back into the statistical approaches to kind of get the best of both worlds. And it sounds like that's what's happening here as well. Yeah,
I think that's right. There's actually a very interesting kind of avenue that people are starting to explore in this area, and I'm also working on this a little bit. So infants, they're not just bombarded with raw audio. Of course, infants also have a lot of other senses, right? Touch and also vision. So there's a group of people, and we're also working on this, that kind of look at if you have, for example, a speech signal, but it's paired with an image. So you have a spoken signal. So it's not a written caption, it's a bit of speech, but it describes an image. Does that image actually allow you to more easily kind of learn the words that's used in the language? So you might have a picture of people skiing or something, and then someone describing that image in speech. And then you can kind of use that image to ground the things that you're discovering. So I think apart from thinking about kind of these linguistic insights, there's also this general question of how can we glue different modalities and different signals together? And that very much operates in a statistical point of view. But again, we need to figure out what are the specific things that we need to build into these models for it to actually learn, because it's a very, very hard task if you don't have labels. It is really interesting how this pendulum actually sways. And I think in the supervised case, if you have a lot of labeled data, then following a kind of a very purist, let's just learn from the raw data approach and learn to predict these labels that we know are important. I think that makes a lot of sense. But if we're kind of going to this low resource case, or in general in machine learning, actually, I think there's a lot of evidence that shows that if you don't have so much labeled data, then building in structures actually helps you in the short term.
You mentioned that the zero resource speech recognition community follows closely what's happening in the cognitive science community. Are there specific examples of insights from that community that have advanced the state of the art in your community?
That is also a very good question. And I didn't say we follow them. I said we try to follow them. We should follow them a lot more. Actually, Emmanuel Depoux, he's a researcher in France, and he really is at this intersection of these two communities. And my supervisor, Sharon Goldwater in Edinburgh, she's also very close to the intersection of these. community. So there's definitely an overlap. I'm trying to think of concrete examples. I think from, I'll give two quick examples. So actually, and I might not do it complete justice, but I'll try. There's a lot of evidence that shows that infants can actually pick up things like syllables. Even before they understand a complete language, they are able to figure out kind of these puffs, right? These little bursts of energy, which are syllables. Actually, if you listen to a language that you don't understand, you would probably, like, I don't know, maybe you speak Japanese, but if you listen to Japanese or Afrikaans or Tsonga, you would probably be pretty good in figuring out where syllables start and end. And human infants are able to do this. So there's a number of researchers which have tried to explicitly build these things into their models, to explicitly use syllables or kind of use that to guide the systems. That's one example. In our own work, what we've been doing is, so there's actually also a lot of evidence that even before infants can distinguish fine-grained phonemic categories, so this is like the minimal sound units, vowels and consonants and so on, before they can actually distinguish these things, or while they're learning to distinguish these sound categories, they can already identify reoccurring word patterns in speech. So if they keep on hearing specific words, they can start to identify kind of larger spanning chunks that reoccur. And that it's quite interesting how psychologists test these things in the lab. So they would teach children essentially, or human infants, like something like Klingon, which obviously the child hasn't heard before, hopefully. And then they would use eye tracking experiments to figure out whether the child has actually learned a specific word. Now, we know from these lab experiments that children are able to figure out longer spanning word segments. And what we've done in our own work is we've said, well, okay, if a child can do this, can we actually build that into our model? So maybe you don't know everything that's going on in the language, but maybe you can run a kind of an unsupervised system that identifies longer spanning words or phrases. You identify these, and then you use these as a signal downstream in building a statistical model or a neural network model to kind of use that information. And that has proven to be very successful.
So when you think about the approaches that are required to do the zero resource speech recognition, can you walk us through the various elements of it and how it differs from the way we might approach speech recognition traditionally?
Yeah, that's also a good question. So it's quite kind of interesting because this is a fairly young community. When I started my PhD, there were maybe 2 groups working on this. And now all of a sudden there's like, 10, which doesn't sound like a lot, but in the speech community, that is actually a kind of a big growth. And it's kind of interesting. I just came back from, just before the Indaba, we had interspeech in India. And there I went to a workshop, spoken language technologies for under-resourced languages. And it was kind of interesting there. If you look at the type of techniques that the zero resource community is using, it's a little bit all over the place. And I think it's because we're kind of trying to redefine the stream that you need to follow, the type of techniques that you need to use, because we're seeing that a lot of the standard supervised speech processing techniques are just not working. If you don't have labeled data, then the trends we're seeing is very different from when you have labeled data. To actually answer your question, so you've asked just about kind of the little steps that we take. I think at the moment it kind of seems like we're converging to maybe 2 big important problems that we need to crack. First, if I just give you a corpus of audio and you need to kind of process that, then the first step you need to do is figure out good, what we call features at the fine-grained level. So kind of standard supervised systems will always start in the same way. They kind of break a speech stream up into these small windows, and you hope that the signal is stationary in that window. Okay. And in a supervised system, what we're seeing now is if you break the speech stream up in this way. And then you feed this into a deep neural network and you tell it that in this little window, this speech sound occurs. Then what the system can do is it can kind of learn what should it extract from this little chunk of speech to identify a particular sound. Okay. And in the zero resource community, it's very similar. The first step is we need to break it up into these little overlapping windows. But then our challenge is we need an unsupervised method to kind of figure out what is it that makes these little speech sounds. And there people are kind of either using kind of classical, they call it Gaussian mixture model based approaches, which kind of tries to identify these small acoustic units, these kind of subword units. And then another group of people are using unsupervised neural networks. And then once you've got features at this kind of fine-grained level, then you need a system on top of that to kind of try and glue these features together to find structures corresponding to bigger units, things like syllables, and then words, and then ultimately sentences. And for that, it's also mixed. Some people use kind of more classical Gaussian mixture-based models and unsupervised hidden Markov models. And I think there's a big push to try and get these neural models, which are working so well in the supervised case, to also kind of work very well in the zero resource case, and using neural models to discover these word units and sentences ultimately.
Okay, so let me try to recap that to see what I was able to capture. So you've got these speech signals, and traditionally we'll like window those and try and within a given window feed that into a neural network, let's say, along with a label, and then essentially train that neural network to match those labels to those little segments of speech. And
that's more or less right, yeah.
In this world, we don't have the labels, so we're kind of capturing these windows, and we're using some number of techniques. Gaussian mixture models are one, neural networks are another. But we're trying to identify patterns within these windows. But are we? I mean, so we're kind of comparing across windows in order to do this. Is that right?
Yeah, that's right. And I think you're stepping through things very carefully. I think that's good. I think the ideal case, what we want is in these kind of short windows, we want to find a representation which captures something like phonemes, kind of, or at least the small set of units that's used in a particular language. So if I give you a big corpus of audio, what you want to find is, can I find features that tells me this language uses a, b, f, okay? And in some other language, there might not be the f distinction. And you want a method to kind of automatically figure out what are the kind of these basic building blocks. So if I take one window and I get a representation for that window, and I get another window, maybe later on, and I get a representation for that window, then I want to know that kind of the fine-grained, the subword unit used in these two windows, are they the same or are they not? That's kind of what it boils down to. And in the supervised case, a neural network can kind of figure out exactly what should it look at in the speech stream to identify the speech sound, because I'm telling it what speech sound to look for. But in the unsupervised case, how do you do this? Because you don't know. So you need to start to think about unsupervised models that can do something like clustering. So a Gaussian mixture model, essentially, if I just give you a whole bunch of these like little windows and I tell you group them according to what you think are phonemes or speech sounds, then you can start to do that. You can train a Gaussian mixture model in an unsupervised way and then find these clusters or these groupings of speech sounds that you think are the units that's used in the language.
How do you even get the window sizing correct? I'm imagining that phonemes have different lengths, and phonemes over some sample of speech, maybe one of them is 2x the length of the other. And so if you kind of choose a larger window, you'll end up with multiple phonemes in the window, or at least maybe the end of one and the start of another. Like, is it kind of a sliding window approach and you're trying to maximize something that tells you that you've got a single phoneme, or are there variable windows? Like, how does that seems like pretty fundamental to this, but also hard.
Yes, it is hard. So actually supervised systems also have this question, like how do you choose a window? Because you need to, so just to answer your question, we always use a sliding window. So you kind of have this window that, okay, you need to pick a length and then you slide it across the speech stream. And in the first systems, you take a window and you take a Fourier transform, which tells you about the spectral content of that window. And you just keep on doing this. So you just slide this across and you look at the spectral content. And now you've got this question of this trade-off. If I make the window long, then I've got a lot of data to kind of tell me what's going on in that window. If I make the window too short, okay, then if I've got a very short window, then I know that it's only going to be one phoneme or part of a phoneme, which is kind of fine. If I only get parts of phonemes, that's also okay. I just need to model that. So I might take a very small window, which means that I know that this is only one speech sound in this window, but then you've got a lot less data to kind of to kind of estimate the content of that window. And this trade-off is something that you don't just see in speech processing. You see it in any type of kind of signal processing task. And luckily, people in the 80s really fiddled with this and tried to figure out, how long should the window be and how much should I move it? And I mean, I can just tell you the answer now because people have been trying to do this for 30 years. And so I think the community as a whole, including the supervised speech community, has kind of settled on a relatively specific window length and then a frame skip. And then, so in the supervised community, you don't care if you sweep this window across and it's just predicting the same phoneme for multiple windows, then you kind of know that you're in a phoneme, and then you transition to the next one. I kind of oversimplified that approach. So what they normally do is they take a window, you predict the label, then you shift the window, you predict the label, shift the window, predict the label. And now what you get is kind of the sequence of posteriors over labels. And that actually goes into another system, a decoder, or something that you can train jointly, which kind of glues these things together and tells you, I was in this phoneme for this long, phonemes stitched together to form words in this way, words stitched together to form sentences in this way, and in the end you get a speech recognizer. One question that raises for me, though, that we've kind of arrived at this answer for the window length and the stride, essentially the step length. That's right. But does that suffer from the same asymmetry in terms of the languages that it's optimized for as speech recognition in general? Like if you're trying to apply these techniques to a language that is under-resourced, could it be that these values that are traditionally used don't work as well, or are they more properties of human speech than of a given language? That's a super cool question, because I think if you read the original papers in the late 80s and early 90s describing these techniques, a lot of these things were inspired by the human perceptual system. So they were kind of hand designed initially. They were hand designed to match what we know about the human perceptual system. So those papers say that these things are language universal, and I think that's not something that people question a lot. But it is interesting if you look at supervised system performance on different languages, then if you use the same amount of data and you compare an English system and you use the same amount of data and you compare that to a Zulu system, the Zulu system will always perform worse, even though it might be trained on the same amount of data. Now, there's a lot of other reasons for that, or there can be a lot of other reasons for that. But it's a very interesting question whether we should actually go back to those first hand-engineered research, because they were all evaluated on English. Although the claim was made that they're language universal, they were all evaluated on English, or at least well-resourced languages. And now we apply these things to Zulu and Tsonga other languages. And we see that it's just very hard to get these systems to work as well as they do on English, even if the experiment is controlled. So this was actually, I spoke to someone from MIT, I think it was Jennifer Drexler, and she said, asked this question, like, are these basic features, this kind of fundamental questions, are they over-tailored to English because the people that wrote the papers were English? And I think the zero resource community is starting to ask these questions or bring that up again, because our systems are even more sensitive to these type of decisions.
You mentioned that in the case of Zulu, which was the example I think you just picked randomly, of systems underperforming when trying to recognize that language, that there are some list of reasons why they do. What are those reasons?
That's also difficult to answer. So I picked Zulu. That's maybe not but I can give you a list of reasons. Very often, so for example, Afrikaans, I think Tsonga as well, and I'm not sure about Zulu, are basically languages that where if we write them down, we often glue words together. They're kind of written as one, right? So in English, if you have two concepts, then they're written as two separate words. But in Afrikaans, when it's one thing, even though it might be composed of multiple things, then we write them as one word. Yeah, so something like narrowband speech processing, right? I just said the sentence narrowband speech processing. Mm-hmm. We'll have a word narrowband speech processing, okay? But in Afrikaans, or in German, you will just write it as one word. It will just be like one word. And for speech systems, that's something that's very, very tricky to get right, because you basically don't know when should I split a word and when should it be one. So that's just one example of a case where it's kind of obvious why the system doesn't perform as well. Another thing is, so in Sotho, for example, we have tones, which you also have in Mandarin. And sometimes that's not marked. So you can't see that there's a specific tone being used when you write something down. Speakers of the language know which tone to use based on the context. But you can't see it. If you're a non-native speaker, you won't know which tone is being used. And that might be one other reason why these systems don't perform as well as English. And this is all apart from the kind of what features do we actually put in it to begin with. Those were just two examples. Code switching is another big example, specifically in South Africa. So a lot of the time what we do is we switch between languages in a single sentence. So very often you would switch between your native language and English and then switch back. So if you just look at the output of your speech recognizer, it just got all those words wrong. And a lot of corpora actually have this code switching in them.
It just jumped out at me that even that code switching alone sounds like an interesting research area for these types of systems. Are there folks out there specializing in that?
Yeah, there are. So actually in the lab downstairs, there's a whole bunch of people working on this. And there was a special session, I think at Interspeech as well in India, just a while ago, focusing specifically on code switching, because it's something that happens a lot in South Africa, because we have 11 official languages and they're kind of all spoken geographically in overlapping regions. But in other parts of Africa, it also happens, and then also in a lot of Asian countries and India, this happens a lot. So people are, I think, like over the last 5 years, maybe people have really started to work on this. And it's not just even in spoken language, also in written language. People, for example, in tweets, would switch between different languages. And that really messes up these NLP systems, which are kind of tailored for a specific language, or in speech recognition, you kind of build a system for one language, and that really messes up the system. So there's a lot of interesting questions about how you build these models to kind of handle arbitrary switches between language.
So I think I was trying to recap your representative flow for low resource speech processing. I think I got to like the beginning of the first step.
Right.
See, we talked about this windowing. We talked about this windowing thing and using Gaussian mixture models to try to determine what phonemes are spoken, or in the case of unsupervised, you're trying to, well, I guess the same thing. You're trying to determine the universe of phonemes and which ones are represented in an individual sample. And if that's close to correct, what's next?
Yeah, okay. So now let's say we figure that out. Now what I give you is, so now I can take a bit of speech and then I can kind of pass it through this feature representation model. And that could just tell me this phoneme is present, this phoneme is present, this phoneme. And you don't know whether it's a phoneme. So it's more like pseudo phoneme or maybe just cluster. Okay. And now you've got the sequence of clusters or sequence of pseudo phonemes. And okay, that's helpful. Okay. Maybe you can use that if you're a linguist documenting a language, then that can maybe, prove insightful. But if you actually want to build a speech processing system, you need to go from that to words, or some higher level unit. And that in itself is quite tricky. And it's because of this reason that you already alluded to, that one word can be 3 phonemes long, another word can be 5 phonemes long, another word can be 2 phonemes long. So how do you group these things according to words? And that's very, very difficult. So kind of the classic approach to doing this is kind of a type of compression model. So what you try and do is you try to say, okay, if I treat these 3 units, reoccurring units as a word, how much does that allow me to kind of compress these sequences? That's just one approach. So, but essentially what you need to do is you now need to add a model on top of these unsupervised discovered phonemes to tell you how you group these clusters together to form words. And there's maybe, I don't know, a handful of techniques that you can use to do this. Should I talk through them?
Please.
Okay. Yeah. So people at MIT, actually, when they started doing this, Jackie Lee and Jim Glass, they had a hidden Markov model, which you can kind of train on top of these pseudo phoneme sequences. And they actually broke down their model. The whole thing is trained in kind of one go. So at the bottom, you've got a kind of a Gaussian mixture model, which you can interpret as finding these phone-like units. And then on top of that, now you've got the sequence of phone-like units. So you feed them into a hidden Markov model, which is kind of like a sequenced Gaussian mixture model. And you treat that hidden Markov model at the layer on top of that as syllables. And then on top of that, now you're getting out the sequence of syllables, and using the sequence of syllables, now you can train another hidden Markov model or have another hidden Markov model layer on top of these syllable layers to model words. And the whole thing is kind of trained in as one big, they used, I think, Gibbs sampling to train this whole thing from the bottom up to the top and so on. And that's one approach. And that seemed to work pretty well if you have single speakers, because that really messes things up. But if you go to multiple speakers, then that becomes much harder. I can tell you about our approach if you're interested.
I am, but I guess it just occurred to me that what's the right way to ask this question? There's like a fundamental thing missing for me, and maybe I need to step back and ground out on the goal of this. We're talking about going from speech to text. Is that correct or no?
No.
Okay.
Okay. Yeah. So
I was wondering whether there's like a then numerical occurs step in here, and I'm not seeing it. So
what you want is impossible, right? So
right.
What you want is you want to ground this in some way. And if you don't have text, you just can't do this.
Can't do it.
Okay.
Right.
Yeah. So why do you want to do this? I'll give you 2 reasons, and then I'll ask you a question of how.
What even do we want to do?
Yeah. So what you want to do is, if I give you a big corpus of audio, then what I want you to figure out where words start and end in the speech stream. I want you to snippet up the speech into these things that look like words. Okay. And then if I tell you, okay, these are the word boundaries, okay, which you've predicted, then I want you to tell me this snippet, I don't know what word it is, but this snippet also reoccurs here and here and here and here and here in my speech corpus. Right. So it's this combination of segmentation, breaking it up into things that look like words. And then the second pass, which is clustering, grouping these words together. Now, okay, so that's what we want to do. You want to know why this is useful?
Sure.
Okay, so
I mean,
there's
I'm imagining that it's useful in that I could take that data and have a prioritized list of words to get someone to transcribe for me, and then start to figure out text, if that's what I ultimately want. But why else would it be useful?
Exactly. Okay, so that's a great use case that you've just described there. But here's two more reasons. Okay, one, if you're interested in how infants do this, then having a model that can do this is useful. So then you can fiddle around with the model, check the type of mistakes that the model makes, and see if then you can go and test in a lab if infants use the same type of cues and whether they make the same type of mistakes. And in that way, we can actually learn something about how humans learn language. Okay. I'm not a cognitive modeling person, cognitive scientist, so I probably didn't describe that well, but that is one motivation. A third motivation is, and this is actually a project that I'm working on with some of the colleagues here, is the following setting where this project is in Uganda. It's actually a project with the United Nations, and they're really interested in very, very specific keywords. They have these systems that collect broadcast news. So it's basically servers that capture radio broadcasts. And then you've got this server full of speech data, but you don't have a speech recognizer in Luganda, the language that's spoken there. Okay. But now, as the United Nations, you're really interested in figuring out what people are talking about in these local radio broadcasts. So what you can do is you can get a small number of people and you can tell them, listen, I'm really interested in education. I'm really interested in maybe specific diseases, maybe in specific disasters, things like that. And I can get a small number of people to give me a bunch of keywords that I'm interested in. Okay. Now I've got my unsupervised model. I can label these keywords that a small number of people have given me. And then what I can do is I can go and search this big corpus of audio and find all the radio broadcasts that contains those keywords. And then maybe I can pass only those broadcasts to an analyst and ask them, please just translate these ones. I know they're important to me. And then we can, figure out what people are talking about in Uganda. I hope that makes sense.
Yeah, no, that does make a lot of sense. And so you were about to describe the approach that you use in your lab to go from the phoneme data to the segmenting.
Yeah. So I actually want to answer another question first. Okay, let me answer this question and then I'll answer your other question, which was about grounding. How do you actually know what people are talking about when you don't have any labels? Okay, so I'll first answer the question about what we use. And this is really a technique that I developed in my PhD with the help of my supervisors. So we basically argued that this idea of getting these fine-grained units and then having a syllable layer on top of that and then a word layer on top of that becomes quite hairy. The whole thing becomes quite difficult. So what we've been doing is we've been thinking about this idea of something called acoustic word embeddings. So I think a lot of people know what word embeddings are. It's these kind of continuous vector representations of written words. And we wanted to take that same idea to speech. So when you're building these language discovery systems, inevitably what happens is you end up having to compare two snippets of speech with each other, but they're not of the same length. Okay, two words are never the same length. Even if I say apple and Sam says apple, then these two apples will not have the same duration. So inevitably you end up comparing things that's of different duration, a half a second to 1 second. So what we started to develop was these acoustic word embeddings. And the idea behind these are basically you take a variable duration segment of any duration and you have a model that just maps that sequence, that chunk of speech, you map that to a single vector. Okay, now if you could do this, what you could do is you can just embed basically all the sequences in your language. You can embed all of them, get vectors for each of them, and now you can easily compare the different vectors. And in very short, what I developed in my PhD is something that kind of does this jointly. It starts by, it basically breaks the speech stream up into things that it thinks are words. It's random. It doesn't know. It embeds all of these. It clusters those things into things that it now thinks are words. And then it goes back and resegments. And it has this kind of back and forth thing. I don't know if that makes sense. And that was a 30-second discussion about something that took me 4 years to do.
Are you kind of iteratively creating this embedding space and then performing some operations on it to try to determine the segments and then updating the embedding space and like kind of optimizing the embedding space, or were you saying something else about this? I kind of picked up on an iterative cycle in there, but I'm not sure what the iterations are.
Yeah, you should have written the abstract for my thesis. So what you just said is exactly right. So you start with like a random segmentation of your input corpus, and then on that random segmentation, you build an embedding space. Now, if I actually have an embedding space, okay, initially it's going to be pretty bad, okay, but I have an embedding space. Then what you can do is you can say, given this embedding space, how should I split up my input stream to kind of have a higher score, if you want, under this embedding space? Okay, so you go back, you resegment.
So let me pause you there. So yeah, you've got this embedding space, and are you doing some kind of clustering within the embedding space?
Exactly right. So I actually use a Gaussian mixture model. I also played a Bayesian Gaussian mixture model. I've also played around with some non-parametric, like infinite Gaussian mixture models to do that. So the idea behind these embeddings are that if you say apple and I say apple, then we're going to have two embeddings, and we want all the instances of specific words that are acoustically the same to end up in similar regions in this embedding space. Mm-hmm. So that's really the goal. But when you start out, you don't know where the words start and end, so you kind of start randomly. And then what you do, so you start randomly, you get all these embeddings, and now you group them. Okay, and you cluster them. I use the Gaussian mixture model to do the clustering. And the idea is that every cluster in this Gaussian mixture model should be a hypothesized word. It should be something that you think, or the model at the moment think, that this group of embeddings, they all correspond to the same type of word, they're the same word. Okay, and initially that's wrong, but that's what you kind of hope where the model ends up. So you cluster. You snap up your speech stream, you embed, you get this embedding space. You cluster in that embedding space using a Gaussian mixture model. Now, under this Gaussian mixture model, I can now say, go back to my input, pretend I don't know where the words came from. And under this Gaussian mixture model, how should I split up the speech stream so that I get a higher score under my current Gaussian mixture model for the embeddings that I would get if I split it up? Okay, so then you break it up. And then you re-embed, and then you build your Gaussian mixture model again. Under that model, you go back and say, given these groupings of words, how should I chunk up my speech to get a higher score? And you just kind of iterate through this thing. And I describe it as this iterative process, but actually it's implemented this one Gibbs sampler. So it's this one model that kind of does things in one go.
The projecting backwards step there, where you are asking the question, given a set of groupings, how could you change the segmentation to improve the groupings? Is that a difficult piece in this, or is that a pretty straightforward element?
No, that is a difficult piece. So that's where I spend a lot of my time. Okay, so there's two answers. It is a difficult piece, but it is also something that people have been looking at for a relatively long time.
Meaning in the context of an embedding space, or in other contexts and it carries over?
No, in other contexts, kind of in computer science in general, but specifically in Actually, it came from the NLP literature. So it actually comes from a different part of literature. So in Chinese, you have this problem that we don't know where words start. Like Chinese, in the way it's written without word boundaries, right?
Mm-hmm.
So in that literature, people have started to look at if I kind of know the words in my language, or I think I know the words in my language, how can I figure out where are the word boundaries in Chinese? And using that same type of ideas, that's exactly what we used here, except that now we're doing it on this kind of continuous embedding space. But the mathematics for that is very, very similar to this question of, if I give you an unsegmented Chinese corpus, how do you figure out where there's words? So it ends up being like a dynamic programming procedure where you basically ask, okay, I'm going to start at the end of my sentence. And then what I'm going to do is I'm going to say, okay, words can be between 200 milliseconds and 1 second. Okay, so you built in that constraint. And then what you do is you basically say, okay, I'll start at the end of my sentence. If the last word in my sentence is 200 milliseconds long, what's the score? If it's 250 milliseconds long, what's my score? If it's 300 milliseconds long, what's my score? Okay, and then you're basically looking for all the possible word segmentations in this range, and then you kind of get an overall score using a dynamic programming method for figuring out where words start and end in the speech stream.
And the score in this case is what?
Yeah, so the score, if we're just looking at the single question of should I put a word boundary here or not, then the score is basically if I chunked up this chunk of speech and I treated that as a word, how likely will that be? How close would that be to a cluster mean under my current clustering?
Mm-hmm.
Does that make sense?
You're trying to set your segments up so that as many of the segments as possible are words, basically.
That's right. You can think about that. It's not really as many as possible. It's kind of like if I gave you a utterance, a whole sentence, and I told you pick places that you want to put boundaries, that if I look at the overall score, okay, so now you put boundaries. Now you have a whole bunch of different embeddings, right? And you want to look at the overall score for that utterance. Each of the embeddings gets a score, and what you want to maximize is kind of the overall score for that specific utterance.
One last piece, you mentioned that as opposed to the multiple phases, you do everything in kind of one pass with Gibbs sampling. Can you give us kind of the high-level overview of Gibbs sampling and how you apply it here?
Yeah, okay, so Gibbs sampling is this very cool technique where you basically try to get samples from a distribution. And in general, that's tricky, especially if your model is quite complicated. So what Gibbs sampling does is it basically keeps everything fixed, and you want to get a sample for a latent variable. So in our case, the latent variable might be something like, which class does this embedding get assigned to? Okay. So in Gibbs sampling, how it works is you pick a specific latent variable, and you keep all your other latent variables, you keep that fixed at previous samples, okay? And then what you say is, given that all the others are fixed, sample this thing from my distribution, this one that I'm interested in, okay? After you sample that one, now you keep this guy fixed and you go to the next latent variable, okay? You keep all the others fixed and now you sample from this guy. Then you go on to the next latent variable and so forth. Does that make sense?
Mm-hmm.
Okay, so in our case, what we do is we basically say, given we've got this entire corpus, the whole corpus have been segmented and they've been clustered already, okay? Everything is fixed and we pretend we know where words start and end, and we pretend we know which clusters they should belong to, okay? Then what you do is you take one utterance in your data set and you say, now I'm going to take this utterance and I'm going to remove that from my model, and I'm going to pretend that this is the only utterance that I don't know the segmentation and the clustering of. So you remove that utterance. And then you say, given the model, which is now defined by all the rest of the utterances for which I know the word boundaries and the clusters, what is the best segmentation for this utterance? Okay. And then what you do is you segment the utterance according to all of the rest of the data that's been fixed, and you cluster that utterance. And then what you do is you fix the segmentation and the clustering for that utterance, and you go to the next utterance. And so basically, your this iterative procedure that I kind of said was like segment, cluster, and I kind of described it at the corpus level. It's really happening at kind of a per utterance level.
Interesting.
And I want to answer one question that you asked really early on, or just a while ago. You asked, if you're just going to do this, right, you're never going to get to text. You're never going to figure out exactly what is the meaning in this utterance, right? You're going to segment that. And that's exactly what's going to happen. I don't know if you saw this movie, Arrival.
Yes.
Yeah, some people loved it. Some people hated it. I really liked it. But there's this scene where they go to her and they ask her, they play her this snippet of audio, right? And she's a linguist. She's a linguist that documents languages. So they play her the snippet of audio and then asks her, listen, what is being said in this language, right? And she looks at them and tells them in a it's probably very un-Hollywood, but tells them, I can't help you, right? I have no idea what this snippet of audio means because I don't have any context. I haven't seen the people that speak these things. I haven't seen when they use it and when they do not use it. And a lot of the research into these zero processing models is exactly like that. We just want to see how can you learn something from the raw audio. And infants can do this to some extent. And our models can do this to some extent. And then there are these good use cases for these models. But ultimately, you can never figure out what does this word actually mean. And this is why a lot of people in this space are moving to the setting where you have other signals that goes with the speech. So if you have a chunk of unlabeled speech, but you have an image describing the context in which the speech is used. Because if you can do that, then you can segment your words, hopefully, and then figure out, okay, this word, I don't know what it is, but I can ground it because I have an image and I can try and figure out what is it in the image that caused this word to being said. So that's a very, very interesting avenue for future work that a lot of people are looking at.
Well, I was going to ask you, if you had some words on where you see this going, but that sounds like you anticipated that question there. Maybe, final thoughts, again, kind of circling back to where we started all this on the Indaba and, what you see for that community and more broadly machine learning and AI in Africa.
Yeah, so I think it's a super exciting time for machine learning and AI in Africa. And the Indaba is one part of that. And that has really started, I think, to build communities and kind of bring people together in Africa and kind of helped people to see that the stuff we're doing here is very, very relevant also at the broader scale. That was quite a broad question, so I'll give a whole bunch of small answers. One thing that I'm very excited about is that in Africa, we have very unique challenges and unique opportunities. And so taking language as an example, there's so many languages spoken here in the same geographical area, and that's very, very unique. And I think what's going to happen if we start to push this community forward, and if people actually believe that they can do this because we can, then what I think is going to start to happen, and I hope for this, is that we're going to start to develop unique solutions for our unique problems. And I think if that happens, it's not just going to be like we are users of machine learning tools that's being developed in Europe. Of course, we need to be that as well. We need to solve our problems using the tools that's being developed in Europe and in the US. But I think if we start to solve the problems here, then we're actually going to start to contribute to the global scene. And we're going to start to say, listen, this is a unique solution. And actually, you guys can also use this in some other problem areas in machine learning. So I think it's going to be a combination of developing exciting applications, but then also contributing to foundational research in machine learning and AI. And I think that's really what I hope will happen. The Indaba is growing a lot. It's going to Kenya next year, which is super exciting. And then Indaba has this kind of dual motivation. The one is to strengthen machine learning and AI in Africa, but then also to fix the problems of diversity in ML. And I hope that is something that Africa can also contribute to, because Google can just start to hire a lot more African researchers, right, from across the world. And I think that would be very exciting. Mm-hmm. For me personally, the thing that excites me most is actually the Indaba spin-offs. I'm very passionate about developing local communities, because I think, so in the Cape area, for example, there's a lot of people working on ML, and we can learn a lot from each other, but up until fairly recently, a lot of people have worked in isolation. So I'm very, very passionate about building local things at universities and in regions. And the Indaba X is a spin-off of the Indaba, kind of funding these local, regional, little Indabas. And I think that's really where we're going to see some interesting things happening, people starting to collaborate, and working together. I'm very excited to see what will happen there.
Fantastic. Well, Herman, thank you so much for taking the time to chat with us this morning. It's really, really interesting research you're doing, and I enjoyed learning about it.
Cool. Thanks so much for having me.
All right, everyone, that's our show for today. For more information on Herman or any of the topics covered in this show, visit twimlai.com/talk/191. For more information on the Deep Learning Indaba podcast series, visit twimlai.com/indaba2018. Thanks again to Google for their sponsorship of this series. Be sure to check out the 2019 AI Residency program at g.co/AI Residency. As always, thanks so much for listening, and catch you next time.